Okay, let's continue our discussion. So in this video, we are going to discuss about satellite, especially Earth satellite. So what is a satellite? A satellite is a body which is revolving around a planet. In a specific way, we can say a satellite is a body which revolves around a planet. Let's take this planet is Earth. Okay. And this satellite is revolving at a height of h. Okay. We have example like Moon is also a satellite. And of course, this is a natural satellite. So, and there are many artificial satellites which has been sent into the space, and those satellites are orbiting around the Earth. So let's take one of those satellites and let's take its orbit to be circular. In this case, there should be a force, centripetal force, acting on this satellite to keep its motion in a circular path. And we know such a force, we call it centripetal force. So this centripetal force is here gravitational pull provided by this Earth. Okay, and we know this centripetal force can be represented as mv square by r, which is from here to here. So it is re plus h, and m is the mass of the satellite, and v is its speed with which it is revolving. Now, gravitational pull is g, mass of the Earth, into mass of the satellite divided by this distance squared. Okay, then we will have v square equals to g me by re plus h, and then we will have v equals to the square root of this thing, g me by re plus h. Okay, so this is the speed of the satellite which is revolving in a circular orbit. Now we can get time period also. So the distance covered in one complete revolution. So in one complete revolution, distance covered will be, let's say it is x. So this should be 2 pi into radius of the orbit, and radius of the orbit is re plus h. Okay, and let's take capital T as time period, which is time taken to complete one revolution. So if we are taking these two things, the speed of the satellite can be given as the distance covered in one revolution divided by time taken in one revolution. And now we have, here we have, let's say, first equation, here we have second equation, and if you compare these two, you will get 2 pi re plus h divided by time period equals to a square root of gme by re plus h. Okay, further we can rearrange the terms, and we will have 2 pi into re plus h, and then we will have multiplied with re plus h divided by g m e, and this should be equal to the time period. This is what we are going to obtain, time period of the satellite. Okay, now we can further write time period equals to, look, we can keep this thing inside here, and then we will have 2 pi re plus h into re plus h whole square divided by gme, and now time period equals to 2 pi square root of re plus h cube divided by gme, and now you can see here it is following planetary law of planetary motion, Kepler's law of planetary motion, and specifically law of periods. How can we say this? Okay, so if we take a square of both sides, here we will have 4 pi square and then re plus h cube. Now you will be convinced. Time period square equals to, this is here it is radius of the circular orbit. In elliptical case, it was semi major axis. So here we will have gm E. So you can write here T square equals to something constant Q Re plus H cube. Now you will have the idea about this thing. Again, it is coming the same. Okay. Now, in case of near Earth orbit, means satellite which is revolving near the Earth surface. So, in that case, let's say near Earth orbit, we can say that Re plus H can be written as Re approximately. And in that case, T equals to, here we have T equals to 2 pi Re cube divided by GME. So I'm writing from there 2 pi and square root of Re cube by GME. And further we can write, if you observe carefully, we can write Re divided by GME and divided by Re square. What I have done, I have divided both numerator and denominator with Re square. And then we will have here 2 pi square root of Re by G. Okay, so time period you can get in this way. Time period of a satellite which is revolving near the Earth's surface, it is 2 pi square root of Re by G, where G is acceleration due to gravity. Okay, this is one thing. And if you put these all values here, this time period comes nearly 85 minutes. And we have an example, such an example like International Space Station. So International Space Station revolves with a time period of 92 minutes nearly, and it is at a height of, on average, it is at 400 kilometer from the Earth's surface. Actually, it varies 370 to 460 kilometer. So, and this value is nearly coming to this one. Look, this H is also present here. If we are going to do more precise calculation, this H is also present here. So the time period will vary with it. But this is an approximation where H is much smaller than the radius of the Earth. So this is what the case. This is a specific example. Now, what about energy of the satellite revolving? So we know that if it is revolving, let me write it, energy. Okay. So if it is moving, it has kinetic energy, and this kinetic energy can be written as 1 by 2 m v square. So we are discussing about this case here, not the near one, but we are taking this h into consideration. So v square will be gme by re plus h. So here we have 1 by 2 m v square, 1 by 2 m gme by re plus h. Now what about potential energy? So we have obtained several times such a thing, minus g m e into m. This is mass of the satellite, and then what is the distance? This. So Re plus h. Now total energy is kinetic energy plus potential energy. So here we have kinetic energy plus potential energy, and this is total energy of the satellite. And then you have to add these two things. So here we have g m e m divided by twice Re plus h minus GME into m divided by Re plus h. And ultimately it will be a negative quantity here, GME m by 2 Re plus h. You can do it by yourself. Okay. So what is happening here? Total energy of this satellite is a negative quantity. And this shows that the satellite is bound to revolve around the Earth. Means it is a kind of inbound system right now. What if this energy becomes positive or zero? So we have done this thing already in case of escape speed, where we have said that if the energy is zero, that stone or that projectile was free to escape. So if this is negative, total energy is negative, then the satellite will keep revolving around the Earth. It will be a kind of bound thing. And if this energy is positive or zero, or you can say if this is non-negative, then this satellite will be free to leave the Earth's gravitational field. And this is what happens when we used to send space probes. Like take an example. So let's take this example of Mars orbiter mission, where look what is happening. This is the space probe, and this space probe is being sent to the Mars. So what is happening? If I can zoom it, let me show you. This space probe is sent to the orbit and to revolve around the Earth. And while revolving, its speed is being increased. And look, its path is also getting bigger and bigger. This ellipse is getting bigger and bigger. And it reaches at a point where its kinetic energy is sufficient enough to overcome the potential energy. Means in that case, the total energy becomes non-negative, and then it flies off, and then it continues on a specific trajectory, and it comes near to the Mars, and where its speed is being decreased, and then its speed is being decreased such that its kinetic energy plus potential energy is now becoming smaller and smaller, means a kind of negative thing. And then when it comes near the Mars and its kinetic energy is not sufficient enough to overcome the negative potential energy here, it bounds to the orbit around the Mars. So this is what happens if we have a system where a body is revolving around another body and it has negative total energy. The body will be bound to the system, and if it has non-negative energy, it is free to fly off. Okay, so this is all for this video. In the next video, we will discuss examples from this chapter.